Imagine losing power during a storm and discovering that the only device still operating in your yard is being powered by the ground itself. No sunlight, no generator, no rechargeable battery pack, just a few pieces of metal buried in damp soil. It sounds like an internet experiment, but the principle behind it has been understood since the earliest days of electrical engineering. Place two dissimilar metals into moist earth, connect them correctly, and a small electrical current begins to flow. This device is commonly called an earth battery. It will not replace the electricity entering your home, and it will not run your refrigerator, but it can create enough continuous power for certain sensors, small lights, monitoring equipment, and other low-draw electronics. More importantly, it can be assembled with ordinary hardware store materials for less than $10. Today, I'm going to explain what an earth battery can realistically do, why moist soil can produce electricity, and how to test a simple version on your own property. First, forget the idea that electricity must always come from a spinning generator or a solar panel. A battery does not manufacture electrons out of nowhere. It creates conditions that encourage electrons to move from one material to another. That movement becomes electrical current. For an earth battery, you need two metals with different chemical properties. Zinc gives up electrons more readily, while copper accepts them more readily. When both metals are placed in a conductive environment, electrons travel through the wire connecting them. The wet soil surrounding the metals completes the chemical process. Ordinary ground contains moisture, dissolved minerals, salts, organic material, and microscopic organisms. Together, these allow charged particles to move between the buried electrodes. In other words, the ground acts as the electrolyte. You may have seen the same principle demonstrated with a lemon. Push a galvanized nail and a copper coin into the fruit, connect a meter, and you will detect voltage. The lemon is not creating unlimited free energy. The chemical reaction involving the metals creates the electrical potential, while the acidic liquid allows the reaction to continue. An earth battery operates on the same basic principle, except the electrolyte is the soil beneath your feet. A single pair of copper and zinc electrodes may produce approximately half a volt to 1 volt under favorable conditions. The amount of current is generally small and varies greatly depending on the moisture, soil composition, electrode size, spacing, and degree of corrosion. That makes one cell more useful as a demonstration than as a practical power source. The situation changes when multiple cells are connected. When cells are wired in series, their voltages are added together. 5 cells producing roughly 3/4 of a volt each could provide close to 4 volts. 10 cells may produce enough voltage for small experiments, although the usable current will still remain limited. Connecting cells in parallel can increase available current, but every cell must perform at a similar voltage. Poor connections or badly matched cells can reduce the output of the entire array. This is why the most useful first step is not attempting to power a device. It is learning how the soil on your property behaves. Some locations perform much better than others. A damp garden bed may outperform dry lawn soil. Clay-rich ground usually retains water and dissolved minerals better than loose sand. Areas near irrigation lines, shaded walls, or downspouts may provide more consistent readings than exposed ground that dries rapidly. Even two locations separated by only a few feet can produce noticeably different results. Earth-powered experiments are also not limited to copper and zinc cells. Researchers have developed microbial fuel cells that collect electrons released as microorganisms break down organic material in soil. These systems rely on biological activity rather than only the corrosion of dissimilar metals. In 2024, a Northwestern University research team introduced a soil-powered microbial fuel cell designed to operate under changing moisture conditions. The device was developed for low-power agricultural and environmental sensors, not for household appliances. That distinction matters. The strongest modern use case for soil-generated electricity is not replacing the electrical grid. It is supporting electronics that need very little energy and are inconvenient to service regularly. Think of a sensor installed far from an outlet. It may only need to measure soil moisture, temperature, movement, or another environmental condition. Replacing its battery every few months can be expensive and impractical, especially when hundreds of sensors are spread across a farm or natural area. A small soil-powered system that operates continuously, even at extremely low output, may be valuable in that situation. The history behind this concept stretches back much further than modern sensors. During the development of telegraph systems, engineers discovered that the earth could be used as part of an electrical circuit. Instead of installing 2 long conductors between stations, they could sometimes use a single wire and allow the ground to serve as the return path. This reduced the amount of wire required over long distances. Inventors also experimented with buried metal plates as electrical sources. Alexander Bain, a Scottish inventor associated with early electric clocks and telegraph technology, explored ground-based electrical arrangements during the 19th century. These systems were never secret household power plants. Their importance was that they demonstrated how soil and the earth could interact with electrical circuits. Natural currents can also move through the ground during changes in Earth's magnetic environment. These are known as telluric currents. During severe geomagnetic storms, unusually strong currents have entered telegraph systems through their ground connections. The Carrington event of 1859 famously disrupted telegraph networks and produced electrical effects powerful enough for some equipment to operate after local batteries had been disconnected. But those rare geomagnetic events should not be confused with the predictable output of a backyard earth battery. A normal copper and zinc earth battery is primarily an electrochemical cell. It does not continuously capture enormous hidden currents from the planet, and installing more rods will not provide limitless energy. The available energy comes with a cost. The more reactive electrode slowly deteriorates. In a copper and zinc cell, the zinc is gradually consumed by corrosion. That is why galvanized nails and rods eventually require replacement. The device may avoid lithium batteries, but it does not eliminate material consumption. With those expectations clear, here is a simple way to test the concept. You will need a length of copper pipe or several pieces of bare copper, galvanized nails or galvanized steel rods, insulated wire, a digital multimeter. Optional alligator clips can make the testing process easier. Begin with one cell rather than immediately building a large array. Choose a location where the ground is naturally moist. Push one copper piece several inches into the soil. Place one galvanized nail or rod nearby without allowing the two metals to touch. Leave a few inches of soil between them. Connect the red lead of your multimeter to the copper and the black lead to the galvanized metal. Set the meter to measure direct current voltage. A positive reading means the polarity is correct. A negative number simply means the meter leads are reversed. Record the voltage. Next, test a different section of the yard. Try a shaded location, a garden bed, or a place with denser soil. Comparing several locations will tell you more than immediately adding additional electrodes. Once you find a reliable location, build several matching cells. Each cell should contain one copper electrode and one galvanized electrode. Keep the spacing and burial depth reasonably consistent. To connect the cells in series, join the copper electrode from the first cell to the galvanized electrode of the second cell. Then connect the copper from the second cell to the galvanized electrode of the third. Continue the pattern through the array. The unconnected galvanized electrode at one end becomes the negative terminal. The unconnected copper electrode at the other end becomes the positive terminal. Measure the entire array before attaching any load. You may see a reasonable voltage when nothing is connected, but experience a major drop as soon as you attach an LED or electronic device. This occurs because voltage alone does not reveal how much current the array can deliver. A weak battery can show several volts on a meter and still fail to power anything meaningful. That is not evidence that the meter is wrong. It means the source has high internal resistance. Electrode surface area can influence output. Larger pieces of metal expose more material to the soil, although simply increasing the size does not guarantee proportional gains. Short, secure electrical connections also matter. Dirty metal, loose wire, corrosion at the connection points, and partially insulated electrodes can all reduce performance. Do not use stainless steel as a substitute for the galvanized electrode. Stainless steel is intentionally designed to resist corrosion. That makes it durable, but it also makes it poorly suited for a basic galvanic soil cell, in which the chemical activity of the metal is essential. You should also be careful about adding salt. Salt water may temporarily increase conductivity, but excessive salt can damage plants, alter the soil, accelerate corrosion, and create environmental problems. It is better to begin with naturally moist soil than to repeatedly pour salt around the electrodes. For outdoor experiments, plain water is the safer first adjustment. After measuring the voltage, test the array with a small load. A low-current LED, sensor, or capacitor charging circuit is more realistic than attempting to connect it directly to a phone or household battery. Many electronic devices also require stable voltage regulation. Even when the average reading appears sufficient, fluctuations may cause the device to restart or fail. A small energy harvesting circuit can collect the limited output over time and store it in a capacitor or rechargeable battery. That approach is often more practical than trying to operate equipment directly from the soil. The earth battery therefore works best as a slow energy source. It produces a little power continuously rather than a large burst on demand. That makes it poorly suited for heating, cooling, cooking, pumping water, or operating motors. Those activities require far more power than a small backyard array can reasonably provide. A 5-watt light running continuously consumes 120 watt-hours each day. Producing that amount of usable energy from simple soil cells would require a much larger and more carefully engineered installation than the inexpensive experiment described here. Claims that a handful of nails can independently run substantial household equipment should be treated skeptically. However, low output does not mean the idea is worthless. Remote sensors, scientific instruments, garden monitors, educational projects, and extremely low-power transmitters can operate within a very different energy budget than household appliances. For those applications, reliability and low maintenance may matter more than raw wattage. An earth battery is also a useful lesson in how electricity actually behaves. It demonstrates voltage, current, resistance, polarity, series wiring, corrosion, and the relationship between chemistry and electrical energy. Unlike a sealed commercial battery, every part of the system is visible and adjustable. You can change one variable at a time and immediately measure the result. Try increasing the distance between electrodes. Test shallow placement against deeper placement. Compare wet soil with dry soil. Compare small nails with larger galvanized rods. Observe how the voltage changes over several days and what happens as the ground dries. The goal should not be proving that dirt can replace a utility company. The goal should be learning where small, continuous energy sources can perform jobs that would otherwise require disposable batteries or frequent maintenance. That is a much more realistic and ultimately more useful way to view this technology. For less than $10, you can build a working electrochemical cell in your yard and see measurable electricity produced through a reaction most people never think about. The ground is not an unlimited power outlet, but under the correct conditions, it can become part of a small electrical system. And once you have measured that current with your own meter, the experiment stops feeling like a forgotten story from an old engineering book. It becomes something real, operating quietly a few inches beneath the surface. Would you use a soil-powered system for garden sensors, emergency marker lights, or simply as an experiment? Leave your most practical idea in the comments. In the next project, we will look at another overlooked use of the ground, using buried thermal mass to reduce temperature swings without running a conventional air conditioner.